Hello, this is Professor Kernler again, and this is our Calc 3 sequence. And today we're talking about section 17.3, conservative vector fields. We're going to do two videos, introduce some definitions of what a conservative vector field is, and then we will, in the second video, do more examples and get some important theorems that will be useful as we progress. First of all, before we do that, we're going to give some definitions here for different types of curves and regions. So let's start here with that. First of all, for some curves, we can define whether it is a simple curve or a closed curve. So here I have some simple curves. I'm going to let's make a little grid. So a simple curve might be something like a little loop or a path like that. And then not simple maybe something like a figure eight or a path that crosses over itself. So simple means it doesn't intersect itself. And then we have closed and not closed. And you can see the difference there. Closed kind of loops all the way around back to where it started. And then we have regions. And we'll do a little bit bigger here. Grid over here. And we have a region like this versus a region, maybe a hole in the middle. So these are both connected. Oops, that's one word. And then not connected might have a couple of regions. Not connected. And then we could have that last one here. Maybe one of them has a hole in it, something like that. So the difference between the two columns here is that when there's no hole in the middle, we call it simply connected. The individual pieces are simply connected, and then these would be not simply connected. It's a little confusing because you're using connected twice. So the region itself can be connected, and so that means it is one continuous region. And then the simply connected is about the little parts. Is there any hole in the middle of any of the parts? That's the simply connected. So just a definition here about curves. Suppose we have a curve and it's defined parametrically. We say there's a simple curve if r at t1 never equals r at t2 for any t1 not equal to t2. And it's closed if r at a is equal to r at b. So simple curve and closed. So here's the definition of a conservative vector field, and that's what we're going to talk about for the rest of this section. It's a definition, it's a conservative vector field if the field is the gradient of some function, some differentiable function, phi. So we were talking about those in the previous section, about gradient fields. Well, if a field is a gradient, we call it a conservative field. So there are some tests for whether a field is conservative. This first theorem, we're going to prove it. We'll prove the two-dimensional version. But if we have a field and it's a vector field on a connected and simply connected region, and all of the components f, g, and h all have continuous first partial derivatives, then it's a conservative vector field if and only if the partial derivative of f with respect to y equals the partial derivative of g with respect to x, the partial derivative of f with respect to z equals the partial derivative of h with respect to x, and the partial derivative of g with respect to y equals the partial derivative, with respect to z equals the partial derivative of h with respect to y. So it's basically all the cross partials are equal, then it's a conservative vector field. If it's only a two-dimensional, then all you need is the partial derivative of f with respect to y to equal the partial derivative of g with respect to x. So a quick proof here. We're going to skip some proofs later. We're going to prove just the two-dimensional version here, just the 2D version. So we need to prove if and only if, so we need to prove both directions. If a vector field f is conservative, then by definition, there is a function phi of xy where f is equal to the gradient of phi. And we know the gradient is the partial derivative with respect to x and the partial derivative with respect to y. And so we're going to use the notation here for f and g. Those are our x and y components of our vector field. Okay, well, the theorem says that the partial derivative of f with respect to y should equal the partial derivative of g with respect to x. Well, the partial derivative of f with respect to y is the partial derivative with respect to y of phi's partial derivative with respect to x. So that's phi xy. But the partial derivative of g with respect to x is the partial derivative with respect to x of phi, the partial derivative with respect to y. That's the other partial derivative. And we know mixed partials are equal. Scroll down a little bit. Mixed partials are equal. So we can say from there, clearly, partial derivative of f with respect to y equals the partial derivative of g with respect to x. We actually only proved one direction. This is an if and only if statement. So we should be able to start with the fact of the partials being equal and work backward. And it's basically the same logic. A lot of these steps are like two directional steps. But just to be clear here, we really just said, okay, if it's conservative, we proved that the cross partials are equal. Okay, so here's how we can use this. Here's the first example how we can use this. We can say, well, first of all, is the function conservative? Or is the field conservative? If it is, find that potential function. So let's take a look here. Here we have from our field, we'll call this f and this g. So let's find the partial derivative of f with respect to y. That's 3y squared. And the partial derivative of g with respect to x, that would be 3y squared. Those are equal. So yes. Now you can kind of guess in the notes when you have a big space like that they probably are. So let me I'm going to make a little more space here. Slide this over here. Okay, so since they are conservative, or since the field is conservative, that means there is some phi so that the field is the gradient of phi. Well, let's see here. The gradient of phi, that's what we're saying, is the partial derivative of phi with respect to x, the partial derivative of phi with respect to y. And we're saying that our field is equal to that. And so that's y cubed minus 2x and 3xy squared. So we're going to try to work backwards and find the original function whose gradient is equal to this vector field here. Here's how we're going to do it. We're going to look at those first coordinates and say, well, the partial derivative of phi with respect to x must be equal to y cubed minus 2x. So let's integrate that then. So phi must be equal to the integral of y cubed minus 2x just with respect to x. Just with respect to x. So that would be x y cubed minus x squared plus maybe some unknown function. We'll call it h of y. right? If we were to take the derivative of that with respect to x, it would just be 0. Okay, well now, that's phi. Now let's take the derivative of that with respect to y. Okay, so that'll be 3xy squared plus h prime of y. But we already know the partial derivative of phi with respect to y. It's up here. So that must be equal to 3xy squared. Well, there's a clear implication there. I'm going to jump up here. Oops, sorry. Jump up here. This implies clearly that h prime of y must be equal to 0, which means that h of y is some constant. So we have it actually, believe it or not. We have phi as a function of x and y must be equal to, and we had it over here, y cubed minus x squared plus maybe some arbitrary constant. And typically in these cases, for the purposes that we have, the constant is going to be irrelevant. And so what we're going to do is we will typically just give one example, one particular phi, and we usually use the one where the constant is 0. But you don't have to. You can use any other constant, but you'll see as you progress here the potential functions that we want are typically when that constant is 0. It just makes our life a little bit easier. Okay, let's try the same thing. Last example in this video, let's try the same thing, but now we have a field that is a three-dimensional field. So we're going to do the same test, but it's the three-dimensional test. So we're going to do the partial derivative of f with respect to y, that's 1. The partial derivative of f with respect to z, that's 1. Okay, then we have to do the partial derivative of g with respect to x, that's 1, so those are equal. The partial derivative of h with respect to x, that's also 1. So far, so good. These are all equal. And then one more. The partial derivative of g with respect to z, still 1. And the partial derivative of h with respect to y, the matching cross one, still 1, also equal. Therefore, yes, our field is conservative. We're going to use the same logic. It's a little more complex now because now we have a three-dimensional one. The variables are x, y, and z. But what this means then is that our field, which is y plus z, x plus z, x plus y, is equal to the gradient of some function phi, which would be the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. We'll start again with the partial derivative of phi with respect to x must be equal to the first component y plus z. So then if we integrate, phi must be equal to the integral of y plus z dx, which would be equal to y plus z, because that's a constant, times x, plus some unknown function of, now here it could be y and z. And I think we usually use, actually now that I think about it, I think we usually, I don't want to use h here, we already have h, so we're going to use c. It's not a constant, but it's like that, kind of like that integration constant. So it's the integration c. Okay, that's our phi. Okay, well, let's multiply that out. So that equals, phi equals xy plus xz plus some unknown function of y and z. Let's do the next step. Let's take its partial derivative with respect to y. That's x plus whatever the partial derivative of c with respect to y is. We don't even know what c is, so we don't know what its partial derivative is. But we do know above what the partial derivative of phi with respect to y is. Okay, that must be equal to x plus z. So this implies then that the partial derivative of cy with respect, or partial derivative of c with respect to y must be equal to z. Well, we can do the integral again. That means that c function, whatever it is, must be the integral of z just dy. So that's yz plus some unknown function here just of z, right? If we were looking at the partial derivative of z with respect to y, that means any function of z, the partial derivative would be 0. Okay, we are getting close. Well, this means that phi must be equal to xy plus xz plus the c function, which we now know is yz plus some unknown function of z. Let's take its derivative with respect to z again. Not again, but let's keep following the process here. So that'll just be, that'll be x plus y plus c prime of z. Just a prime here, don't need a partial derivative because it is only a function of z. But we know phi sub z. We know that. That is x plus y. We know that from our gradient with the assumption that this was the gradient of phi. That must be equal to x plus y. And so again, like the last one, that implies that c prime of c must be 0, which means c of z is some constant. We'll call it capital C. So let's move over here. Therefore, phi as a function of x, y, and z must be equal to xy plus xz plus yz plus a constant. We can use any constant. Let's use the constant 0. Okay, so there is a full procedure in your textbook. I like to just use an example. I think that's easier. And so that is it for this video. In the next video, we'll dive into some deeper theories and some theorems that we can use to determine whether something is conservative, and then some important consequences if a vector field is conservative.